Hi guys, and welcome. This is module C3292, and this mini eLecture refers to capillary electrophoresis and is for experiment 4A. So the structure is broadly like all of the others of these mini eLectures, and it's on the screen now. References, as for most of the others, as a general analytical textbook, I would recommend Skoog and Company. Skoog et al. More formally. Really good, useful book. Very readable. However, for this particular area, I would recommend Lai's book as well. It's not as readable as Skoog's book. It's a bit denser, it goes into a lot more detail, so if you're interested in capillary electrophoresis, I would also recommend the second reference on the screen. Okay, so again, broadly as in other lectures, this eLecture is not about how to do the experiment. That's why you've got the experimental script. There are references in it, so for instance we're using a particular type of electrophoresis, capillary zone electrophoresis, therefore we'll talk about it. But beyond that type of level, I won't be talking about the practical. I'm also not going to be talking about the operational aspects of the equipment you're using. How to turn the equipment on, how to use it, how to get the data off, how to shut it down. That's covered in the video presentation on capillary electrophoresis. So, in this mini eLecture, as in the others, I'm going to be talking about the underlying theory. However, remember that in your second year in CM3292 Analytical Chemistry, you should already have dealt with this basic theory. So what I want to be doing is not repeating it, so you won't hear me talking about plate theory or anything like that, but just highlight some of the aspects of this method. Okay, let's proceed. The pretty picture here is DNA separation and analysis by one of the families of the electrophoresis techniques. Some of those various methods are particularly good at large molecules, and so DNA clearly is a large biological molecule, that's fine. Some are less so. It's probably worth saying that capillary zone electrophoresis is probably the most widely used electrophoresis technique at the moment. Okay, so this you probably already know. We have a pretty picture. We have an anode and we have a cathode, and between that anode and cathode is a very fine capillary tube, a narrow bore capillary, and the whole assemblage is filled with a buffer, electrophoretic buffer. A voltage is applied between that anode and cathode, and then one gets movement of ions at different rates toward the electrodes. Now, the separation on with capillary zone electrophoresis is based on the difference in electrophoretic mobilities, resulting in different velocities of migration of ionic species in the buffer contained in the capillary. So it's those different the different velocities of movement which are the basis of the method. So let's think about what determines the movement of those ions. The rate at which ions move in this system is clearly dependent on their size and their charge. Before we continue there, we should just make sure we're all on the same page. So this little cartoon has a top and a bottom, and I'm looking at the top at the moment. Effectively, we have the wall of one of the walls of our fused silica of our capillary, which is on the inside comprised of fused silica. So from the wall you have the oxide ions sticking out into the inner diameter, and they are of course negatively charged. So if we think of this as a sort of graph, and we're going to move out from the side of the tube, immediately on the side of the tube you have a layer of negative charge. Now clearly the solution contains positive and negative ions, and this negative charge will attract the positive ions to it, and you can see in the diagram that we've got associated with that negative charge some more tightly absorbed cations, positively charged ions. As one moves further away from the wall, this charge slowly diffuses, and eventually you get to the bulk solution where you have positive and negative ions in broadly equal ratios. So from the wall of the capillary you have this double layer Helmholtz effect, where you have a layer of negative charge with a layer of positive charge, and then the positive charge slowly falls off as you enter into the bulk solution. Okay, so that's the system we're starting with. We now actually apply a potential difference between the anode and cathode of this cell, and unsurprisingly ions of one charge move to the electrode of opposite charge. It's worth noting that this is a driven cell. Anything that you apply a potential to is a driven cell, and in those cells the anode has a positive charge and the cathode a negative charge. You'll remember with thermodynamic spontaneous galvanic cells from your electrochemical studies that in those situations the anode has a negative charge and the cathode a positive charge. But this is a driven cell, and there are two mechanisms for the mobility of the ions, and we'll think about those in a moment. So we'll think of the first one, electrophoretic mobility. It is reasonably trivial, I think, that if we apply a voltage across the cell, then anions and cations move towards their oppositely charged electrodes. Now, this is electrophoretic mobility, actually the one we're interested in, and that's entirely dependent on the nature of the ion, how large it is and how charged it is. This is usually expressed as a Stokes radius, and on the screen you can see the definitions of that. I won't go on and define the terms, I think probably you've met them before. So that's the one we're interested in, electrophoretic mobility. It's really the basis of the method. However, let's imagine that we turned the equipment on, actually as you're going to do in the practical, and you're not going to have a sample to start with. You would find the buffer system would still flow. This is electroosmotic mobility, and you can think of it as simply the result of having the fixed charges on the inside of the capillary tube, which gives you effectively a sort of a driver to drive the sample through the capillary. Electroosmotic mobility is independent of an ion, is independent of its solubility, of the solute rather, and this is not the mechanism that we're really interested in. Okay, I've listed a couple of factors that affect electroosmotic mobility. The inside of the tube of the capillary with its charge structure is crucial, and effectively the double layer inside the capillary, which has resulted from the silanol group ionization, these dangling oxide ions attract cations and gives you that double layer, which is the basis of electroosmotic mobility, but I think we've already talked about that. Okay, why use it? Well, if you compare it, for instance, to ion chromatography or any other of the chromatographic techniques, actually, you get very, very sharp peaks relatively with capillary electrophoresis. It's largely because if you think of, let's imagine we're thinking about gas chromatography at the moment, you get a parabolic front of flow through the column. But here, with capillary electrophoresis, you don't get that at all, because that parabolic flow in GC is caused by the edges of the column, and effectively a Gaussian mechanism. But with CE you don't get that, you get laminar flow. So you get a front of your analytes, in this case our ions, moving through the capillary at the same time. And there's a little sketch graph here showing you how different the resolution actually is. Okay, let's think for a moment then, if you want to fine-tune capillary electrophoresis in terms of getting the best possible separation that you might want to get. It's all about the characterization of the silanol groups on the inside of the capillary. The more ionized silanol groups you have, the larger diffuse layer you'll have, and effectively the faster the flow. You don't get as much resistance in the capillary. Now, the concentration of these ionized silanol groups you can control. Temperature, yes, but pH crucially. Remember that the surface of your capillary, well, let's go back. In inorganic chemistry, by now, you've no doubt been interested in structural defects, so shocky defects or screw defects. Very interesting and useful they are too. But we need to step back now, because the largest defect that any solid material has is its surface. So if you put a lump of maybe silicate mineral, or in this case silica, into an aqueous solution, you have all of those unsatisfied valences and groups in the solution. Therefore hydrogen ions mostly, but with some minerals it's hydroxide ions, are attracted to the surface in the way we've talked about for the double layer. You've not applied any potential here, this is spontaneous. Now what you end up with is a surface charge on the mineral. It's also called the 0 point charge, and it's much the same here. By changing the pH, tuning the pH of the buffer, you can modify the concentration of ionized silanol groups, and that's one of the very important fine-tunings that are crucially important in this occupation we call analytical chemistry. I'm going to make no comment about the analytical CAD. Okay, so here's a summary which I hope makes some sense to you. I'll leave you to walk through it. I think I've said everything I need to say about this now, so enjoy the practical. Take care. Goodbye.